on a more normal schedule, and I'm pleased. I'm episode 7 now, so we're making progress through the Star Wars universe. And so, like I say, it's the 2 65-minute ones, the standard start time for the second talk, and then also Jessica in the afternoon will start at 2, and then we have the panel at 3:30. So what I'm going to talk about today is rigidity theory. And so to get started, in fact, so what I'm going to do is basically in the first talk, you can see that the title is the geometry, and then, so that's the first talk. The second talk, I'll switch to combinatorics, and then Jessica will come and sort of give us a lot more what's going on with a broad overview. And it turns out that in the second talk, that when I do the combinatorics, matroids are going to play a role, and so that's where the relevant poster is Christopher's, because he defines this new invariant the volume of a matroid. So if you're intrigued by matroids and want to learn more, check out his poster. So the plan for the geometry is, first I'm going to talk about sort of frameworks, rigidity, and this is pretty much just an introduction, and so there's various different types. There's bar and joint, bar and body. There's other kinds of ones as well that Jessica might tell us about. And they'll talk about motion. And of course, rigidity means we don't want motion. And what does that mean? And there's local rigidity, infinitesimal rigidity. You'll see there's a matrix that gives us a lot of good information. This gunk on the board is how that matrix interacts with some stuff. And then actually, besides the local and infinitesimal, there are other flavors of rigidity that we'll also play with. And then I'll do a little bit of some of the algebraic geometry, and I'm going to focus on bar and joint frameworks. So there's some varieties going on, and the so-called configuration variety, the Cayley-Menger variety, and what's interesting, this is a nice projective variety. It has a degree. That degree helps us count minimally rigid frameworks. So the idea is we actually get to use some very classical algebraic geometry to give some information about some of these frameworks. So just to get started with a bar and joint framework, I'm going to take a simple graph, and I'm going to use this standard notation for the bracket n. It's just a set from one to n. And I'm just going to think that's my vertex set for the graph, and no multiple edges, no loops. And then a bar and joint framework, so it's going to live in some Euclidean space. So I need a bunch of points in the Euclidean space. And then I also want to add on the line segments determined by the edges of the graph. And so here's a framework in the plane. It turned out later we'll see this guy's rigid, but not infinitesimally rigid. And then, for example, here's something that we have some experience with, a framework that's sort of important to our sort of wakefulness in the morning sometimes.
This is your rejoinder to me passing out espressos?
That's right. I mean, the point is I'm proving that, it's mathematically relevant. And the bar and body framework's a slightly different beast. So we still have a graph, but I now will allow multiple edges. In fact, the multiple edges are pretty important. I don't want any loops. And so a bar and body framework, well, the bodies are rigid bodies. And so, like, for example, in the Stewart Go platform, that's the upper platform, that's the base. Those guys are rigid, they don't move. And then they actually have sort of a three-dimensional extent. It's more than just a single point. And then the bars are line segments, and what they do is they will, and so basically, so it's got to be E has to be an edge in the graph, and I and J are the bodies I'm connecting, but the idea is that I allow different connection points. So in this case, the underlying graph has 2 vertices and 6 edges. And basically each edge gives me one of these things. Now in a Stewart Go platform, what we're going to typically think about when we do this is we typically think about these line segments of a fixed length. But for a Stewart Go platform, you can sort of see there's hydraulic joints here that can sort of move the lengths of the legs, and that makes them interesting for things like flight simulators and other things. Here's basically a microwave antenna that's a Stewart Go platform. So these guys have lots of interesting applications. Now I'm going to focus mostly on the bar and joint ones. And it turns out, some frameworks move, some don't, and sometimes whether it moves or not depends on the dimension. So for example, if I take this square with a diagonal, well, if I happen to be in three-dimensional space, I can just basically just take this upper triangle and just flip it over the diagonal to the lower one. So this guy moves. Whereas in this one, if I'm in the plane, basically the only way to move this thing is just to move the whole thing by a rigid motion. And so this one we're going to sort of call rigid. Here's one, of course, that does move. This was the 4-bar mechanism. And the point is that all these lengths are fixed. And but the point is that and even if I fix these points right here, it still moves because I can rotate around that, and that's what gave us this nice curve that we talked about on Tuesday. But for example, here's a complete graph in RD, and basically once I specify the edge lengths, doesn't matter what dimension I'm in, this guy, the only motion is a trivial motion. So to really nail down what's going on, we have to say a little more. Well, actually, I do want to give one more example of something that moves. And so I talked about the Stewart Go platform. Now, suppose I do actually fix those edge lengths. And then it turns out that it's, in fact, you'd say that this guy is locally rigid. It won't move, but it can have different configurations that have the same edge length. In fact, you can have up to 40 platforms that have the same edge lengths. But it turns out that if you do something more special, so there's a Griffith-Stuffy type 1 platform. So in this case, the upper and lower bodies are equilateral triangles. The attachment points are the vertices and the midpoints, and you sort of alternate. You attach a vertex to a midpoint to a vertex, and just go around. And it turns out this guy, so once I lock the edge lengths, turn this into a bar and body framework, this guy moves, and this is a wonderful picture made by Doug Arnold and Charles Wampler. There's 1 degree of freedom, and so if I were to sort of, put a little thing up here and let this whole thing move, this would trace out this really pretty curve in three-dimensional space. And it turns out this is another one of these images that we've actually seen before, because if you were at the IMA in 2006, it turns out this is an image that there was a tutorial on algebraic methods in engineering, where Rampler was one of the organizers, and so they created this for that image. Also, if you look at the poster for the whole IMA, this features prominently on the poster for the whole year. And then, of course, it's also on the cover of the SIAM Applied Algebra and Geometry Journal. And so we've now sort of seen 2 of these things on the cover, sort of up close and personal. But now let me go back to that question that said that we really actually have to understand what we mean by a motion. And so again, and I should say that here's the notation I'm going to use. So when I have my graph, it's always going to be vertices and edges. And typically I'll let n be the number of vertices and n be the number of edges. And so the idea is that when I take my bar and joint framework. So basically what it comes with these points, and then I also know these lengths. So those are the lengths that I'm interested in. And these are the lengths for the, for the edges in the graph. Those are the ones I want to preserve if I move it. I don't care about, if Qi and Qj aren't connected by an edge, I don't care about their distance. These are the only distances I care about. So you can think about sort of a differentiable family of frameworks. So, now I let my points depend on a parameter. And of course, at time 0, I want to be my original framework. And then, basically for all time, I want to preserve the edge lengths for the edges that I care about. And so that's what it means for a motion of a framework. And all the examples I did earlier sort of are that kind of motion. And, but of course, there's this idea of the trivial motion where I just move the whole thing. And so that's where the special Euclidean group comes in. And so it's basically, it's the group of orientation-preserving isometries of d-dimensional space. It's a semi-direct product of the special orthogonal group and the translation group. And so we add up the dimensions. The special orthogonal group has that. Translations, of course, are dimension d. And so this binomial coefficient is the dimension of our special orthogonal group. And you'll see this many times. For example, there's a couple of theorems I have on the board, and there's our special Euclidean group sort of making its appearance in some of the basic results. And of course, in the case of the special Euclidean group in three-dimensional space, basically, the SO3, it all consists of rotations. And then so this is sort of an especially nice case. But it turns out that sometimes I'm going to simply talk about just up to congruence, and there I allow myself reflection. So every now and then we sort of use the full Euclidean group, and of course, this guy has index 2 and that guy. And so that makes also an occasional appearance in what I'm going to be talking about. Now let's talk about a trivial motion. So a trivial motion is I simply take a path in the special Euclidean group, and I want my path to start at the identity at time 0. And so then if I take that path and I apply it to my configuration, then I get sort of a motion of my configuration. It certainly preserves all the edge lengths. So in particular, it preserves the ones for the edges in the graph. So this is basically a rigid motion of the whole framework. So this is what we call a trivial motion. And so just the definition is that a framework is flexible if it has a non-trivial motion, and otherwise, if it has no non-trivial motions, we call it locally rigid. So I can't move it just a little bit. I might be able to do something, far away that, has the same edge lengths I care about, but I can't get from one to the other, by these sort of continuous motions. And so that's why there's a difference between globally rigid and locally rigid. And here's a common situation that suppose my graph has a subgraph, such that when I look at just sort of the Barger configuration for the subgraph, suppose that part is locally rigid. So suppose that part I can't, the only way to move that particular part is by a trivial motion. Then what happens is that then the two following things are equivalent. If I want to analyze local rigidity for the whole framework, it suffices to think about, to basically take a motion that fixes all the stuff in the subgroup, and if you can prove that something that fixes everything in this subgraph, if that then fixes the whole framework, then I actually, that basically proves local rigidity. So that's a little easy argument. And you'll see that this is going to simplify some of the examples I'm going to do. So here's the first example. So here's a framework I want to claim that's locally rigid. So this is in the plane. And so, I've given you, the points. So it's basically two triangles where I connect edges. And it's pretty carefully chosen because if you continue these edges, they meet at the origin. So that says that this is actually a pretty special configuration. And of course, notice that the outer triangle, that's clearly rigid because it's a complete graph, and of course, basically any complete graph is rigid in any dimension. So the idea is by my lemma, I can basically, if I'm going to prove that this is locally rigid, it suffices to take motions that fix the outer triangle. So the question is, if I fix the outer triangle, can I wiggle the inner one? That's the question we have to answer. And so here's the proof, and it's just algebraic geometry. And so the idea is that, again, I've got things fixed here, and so and the part in gray is sort of the original configuration, and so here I'm trying to suppose that I can move it now. And of course, since I have to preserve these lengths, the point A has to stay in this circle, the point B has to stay in this circle, the point C has to stay in this circle. And if I give names to the coordinates of A, B, and C, then in fact the first three equations are just the red circles where A, B, and C lie. Then of course the other thing I have to do is that I have to preserve the edge lengths from AC, AB, and BC, and that's what the next three equations are. So 6 equations and 6 unknowns. And I just do elimination. I did this in Mathematica, and I got this, fifth degree equation. And then when I asked for the roots, I got 5 roots. And of course, these I'm not interested in because, they're complex. Now, that's negative, but notice that, if x1 were negative, that'd be way over here. And so clearly when that's the case, then some of the others are going to be complex, because that just can't work. And similarly, if x1 were 5.8, that just can't happen. So in fact, x1 equals 1 is the only possibility. And so then to see what happens when x1 equals 1, I then plugged in x equals 1, computed a Grosvenor basis, got this slightly simpler Grosvenor basis, and of course, not surprisingly, this says, hey, x1 is 1. And then, of course, this says that y1 is 1, and of course, that puts me at that point right there, and then, once you have that, once you have y1 is 0, then you easily get the other ones, and that actually forces A, B, and C to actually be at those rest positions. So in fact, that's the only solution, so that proves, in fact, if you think about it, this actually proves global rigidity. And so...
because just having discrete roots, just having a limit that's non-zero tells you that it's locally rigid.
That's probably good. That's probably true. Yeah, I'd have to think about it, but I suspect Frank is right. But what's interesting is when you think about this like in algebraic geometry, you say, oh, but y1 is y1 is not really 0, y1 squared is 0. That says there's something infinitesimal going on. That says that infinitesimally it's trying to move in this direction. So that suggests that, in fact, you'll see later once we introduce infinitesimal rigidity, this guy is not infinitesimally rigid, and this is sort of one way to see it, but as we'll discover, there's much easier ways to check infinitesimal rigidity. And so in fact, that's the next thing to talk about. So we have our framework, and we have the edge lengths we want. And then if I have a motion, then what I can do is I can take the derivative of the motion and of course evaluate it at 0. So this is sort of the velocity vectors of the points. So this is how the points want to move. And then the point is, if I differentiate this equation right here with respect to t, because again, my motion, because this is always equal to a constant, so that's a classic evaluation. So I differentiate set t equals 0, and I discover that this vector is always perpendicular to that vector. And so basically, infinitesimal rigidity means that the only way to solve these equations is when the solutions come from trivial motion. So that's the notion, that's the definition of infinitesimal rigidity, that basically if it wants to move, then that motion actually comes from a trivial motion. So, and so that means that infinitesimally there's not going to be any non-trivial motion. And a theorem that was proved by Asimov and Roth in 1979 is that if you have infinitesimal rigidity, then that actually implies local rigidity. So you have a one-way implication. Although, as we'll see, the example I did before shows that the converse is not true, that you can have local rigidity but not infinitesimal rigidity. And in fact, here's the example, so let's work it out. And so again, we've proved that this guy is locally rigid. So now let's work out the infinitesimal rigidity. I'm going to use my same approach to fix these guys. And so that means that these derivatives are 0. And so basically it's only A, B, and C that are moving. And so it's A prime, B prime, and C prime I have to worry about. And so, so the first equation, it would be A prime minus D prime, but D prime is 0. So the first equation is this. And of course, A minus D is just horizontal. So that means A prime has to be perpendicular. So it's just, some multiple of E2. Similarly, you get B minus E times B prime minus E prime. E prime is 0. And so you get this, so B prime, and so B minus E is this. So it has to be some multiple of E1 minus E2, and same for C prime. So I actually sort of have little formulas now for these guys, and then when I plug these formulas into this, I discover some relations, and that has a non-trivial solution. And for example, I could take alpha to be minus 1, and then beta becomes minus 1, and then gamma becomes 1. and that's the solution that I drew right here. So I actually have an infinitesimal one. So it wants to move, but it can't. And of course, that's what we saw with the algebraic geometry with that y1 squared. But here, it's just a lot easier, just linear algebra. And so that's sort of the power of this idea of infinitesimal rigidity. And of course, what happens is that what made this work is, again, when I said when you connect these three lines, they meet at that point, and that's sort of what makes things happen. And if I sort of were to just jigger the initial configuration a little bit, then infinitesimal rigidity wouldn't hold. And in fact, what happens is that for these two concepts to diverge, it has to be a special configuration. Generically, they really are the same. So it turns out that rigidity was pretty cool, so let's turn it, and that came from linear algebra. That says, let's make a matrix out of it. We've seen matrices are good things. They had lots of uses in other days. So again, here's this notation I'm going to be using, and again, I've put it on the board in case you forget it. And so in this case, I'm going to actually just look at the linear map I get, and so basically, so this is fixed, and now I'm going to regard these now as the input vectors, and so basically, so this now is an element here, and this sort of map right here that is going to basically do our rigidity equations. It just maps this bunch of vectors to this bunch of inner products, and it's indexed by the edges, and the end there, remember, that's the number of edges. And so remember that and so basically you just take what I'm doing is I'm taking these equations and just representing them by a matrix. And then, so this is the linear map, and then when I take the matrix of this with respect to the usual bases, I get what's called the rigidity matrix. And so our first theorem is right here. And so it says that if my framework affinely spans RD, then I have an upper bound for the rank of the rigidity matrix. And what happens is that if I'm infinitesimally rigid, then basically that bound becomes sharp. And I've put that theorem right here on the board because I'm going to want to refer to it a couple of times. And so that's really our first theorem. And the proof is pretty harmless. And so you take the initial velocity vector of any motion, it gives an element of the kernel. This includes the trivial motions. So when I look at the nullity of this matrix is just the dimension of the kernel of the linear transformation, but this kernel contains the trivial motions, but because of this assumption that Q affinely spans RD, this group acts faithfully on the configuration, and so what that means is that its dimension shows up in this kernel of D plus 1 over 2. So what I get is the nullity of this map is at least that binomial coefficient. But now notice that what is this linear map? It maps R to the n times d to Rm, and so if you apply the rank nullity theorem, that I've written it down right here, just in case we've forgotten our linear algebra, and so what happens is that so this guy is greater than or equal to the binomial coefficient, and so that means this is less than or equal to this minus the binomial coefficient, and that's just the first statement of the theorem. So that's, as I said, that's pretty elementary. And then what happens with infinitesimal rigidity? Well, remember infinitesimal rigidity said that the only stuff in the kernel comes from trivial motions. That means that the kernel, that means this actually becomes an equality. And when that becomes an equality, and so that's if and only if it becomes an equality, and so that means, but when that's an equality, then again by our little calculation, that turns that into that, and so the second part is equally easy. And so we get this really nice fact as we begin to learn something about sort of the rank of this matrix and sort of what infinitesimal rigidity. The idea is it really tells us something interesting about that matrix. And now the corollary is just the observation that this rigidity matrix, M is the number of rows of the matrix. And so so for example, what is the first? So the first thing says, well, suppose it has linearly independent rows. Well, that says that the rank is equal then to the number of rows. But then, hey, I have that result with the rank is m, so that turns into that. So instant corollary. And then what about when I'm infinitesimally rigid? Well, infinitesimally rigid says that the rank is equal to this, but the rank, it's always bounded above, because the rank is the row rank, so the number of rows always gives an upper bound to the rank, and so this is also an instant consequence. And so this little corollary really does follow quite easily from that. And then this shows that, first of all, this is an interesting number. This is going to crop up in lots of places. And so you see that basically what happens is that, infinitesimal rigidity tells us something happens one way, but when the rows are linearly independent, the inequality goes the other way. And what we're going to see is that this is deeply implicated in what's called the rigidity matroid. So when we start talking about matroids and linearly independent sets of a certain sets of vectors, this is going to be a big deal. So this is how some of the matroid theory is going to interact with the rigidity theory. And so we're sort of setting the stage for some stuff that's going to come together pretty nicely later in the talk. Now, I said there were flavors of rigidity. And so, we've already talked about local rigidity and infinitesimal rigidity. And of course, global rigidity means that if I have any framework with the same edge lengths, then it's actually just plain congruent to Q. And so, for example, it turns out our earlier analysis makes it pretty easy to see that this guy is, and again, working in the plane, this guy is actually globally rigid. Here's something that's locally rigid. It's two triangles. So in the and again, I'm assuming I'm in the plane. So in the plane, I can't do anything. But this has the same edge lengths. And so in terms of it has the same graph, same edge lengths, but I can't get from here to here by a congruence. And so that's locally rigid, but not globally rigid.
But it isn't rigid in R3.
That's right. Yeah. So in R3, and so in R3, these guys would be related. So again, rigidity is very dependent on the dimension.
So if you have something that's locally rigid but not globally rigid, you can always embed it in a high enough dimensional space.
And then my answer for a lot of questions like that today is going to be ask Jessica.
There's something called universal rigidity.
All right.
So, and that means rigid in all dimensions.
I think David's example on the left, that you go to R3, it still doesn't move.
Yeah, so that one I think just because of the way this one fits. So I think this is an example of one that's universally rigid, for example, whereas this one isn't. So that's yet another flavor of rigidity that sort of persists in dimensions. Or did I just say something stupid?
I think if you think of that as a prism, it might move. Like not that embedding.
Right. Yeah, for this particular embedding.
Yeah, that pretty good bet.
Yeah. But then there's also, a lot of these have minimal versions, where the idea is that you might want something that has one of these properties, but then the property fails if any edge is removed, because removing an edge might give you more ways something could move. Turns out all of these are actually minimal, and so some of the results in theory talk about sort of something that's minimally rigid. And then there's generic versions where you assume that your embedding is generic. So this guy is not generic. So this is a really special kind of thing. Whereas this one in the plane really is generic. And then there's also, of course, combinatorial rigidity. That's something we're going to play with in the next lecture. And now, so that's sort of the background we need for the time being in rigidity theory. And I want to go next to some algebraic geometry. So I'd like to see some algebraic varieties. So again, we have our bar and joint framework based on the graph G. And then the point is that I have this length squared map. And again, it sort of depends on the dimension and it depends on the graph. And so I just map, basically I map a configuration into its edge lengths. And then if you think about it, what we're really interested in is, so basically if I'm given a configuration, it has a bunch of edge lengths, and then the configurations I'm interested are the ones based on the same graph with the same edge lengths. and that's really just the inverse image of this guy. And so it's a real algebraic variety, and it's all frameworks for G with the same joint lengths as Q. And again, the joint lengths I care about are the ones indexed by the edge set E. And so now we're doing some real algebraic geometry. And then that's upon, it's early in the morning, but we are over the real numbers. And but what's nice is when you take the derivative of this map. So when you take the derivative of this map and divide by 2, you get exactly the rigidity matrix. And so that shows that things interact pretty nicely. And then what happens is that suppose that the rigidity matrix has rank n. So in that case right there, so we've already seen that's interesting. Well, if it has rank n, that means this guy has maximal rank. And so just by the implicit function theorem, basically the configuration variety is smooth at this point of that dimension. So we actually know the dimension. So that's why sort of say this condition having rank n, which is that condition, which again is going to be an independent statement in a matroid, that gives us geometric information about the configuration variety. So that we really like, and that's very nice. So let's do a theorem now. And so are the edges of a convex polytope in R3 rigid? So you take a three-dimensional convex polytope. I just happen to have one right here. It suffered a little bit. I should have checked it. So this one is not only not rigid, it's broken. So you have this guy right here, and but it fits together pretty nicely. I practiced. So, I'm going to ignore these guys. So basically, I have these vertices, I have these edges. So this is, so clearly there's a graph, and this gives a particular, framework in R3 that supports that graph. And so the question is this graph rigid? And the point is that this is locally rigid for this graph if and only if every face is a triangle. So the answer to this poor guy is this guy is not rigid because in fact it has no triangular faces. And so how do you prove that? And so it's an if and only if. So it turned out it's proved by Asimov and Roth in '78 using an earlier result of Hermann Gluck in 1975. So going one way, let's try a motion. Well, so here I'm assuming that every face is a triangle. So let's assume that every face is a triangle. And so what I get is I get a motion that takes P to another polytope. And again, things might wiggle around, presumably, but the point is it's going to be to another convex one. And I want to have, because again, I'm taking a small motion. So that's the crucial thing. I'm not taking a huge motion. If I had a huge motion, I could do things. If I start with something convex and take a little tiny motion, it's still going to be convex. And, but what happens is that the faces are triangles. Those are rigid. So that means that I have these two polytopes where they're combinatorially the same, and the edges, when I match them up, are actually congruent. And then there's an 1813 theorem of Cauchy that says that the polytopes are congruent. And his proof is so good, it made it into the book. And so if you look at that wonderful book, Cauchy's theorem, it's a modern version, but it's basically Cauchy's proof, and it's very nice. Now going the other way, so now I'm assuming I'm locally rigid. I need to prove that every face is a triangle. So how do I do that? And so the first thing is we just cite luck. And so the idea is that because Q comes from a convex polytope, basically the rigidity matrix has maximal rank. So that's his first theorem. And again, the convexity plays an important role in his proof. And so we're in that situation right there. So we like that. And but then remember we said that, but that's the situation that gave us the dimension of the configuration variety. So in fact, by one of the earlier slides, you know the configuration variety that is smooth of this dimension, and because remember that it was d times n, but d is now 3 because I'm in 3-dimensional space. And so I have that, but the point is I'm locally rigid. So my configuration variety near Q just consists of trivial motions. And of course, and I'm in a situation where, I'm a 3-dimensional polytope, so I have to span, and this is 6-dimensional. So that means that locally near Q, local rigidity says the configuration variety has dimension 6. So here I get this number is equal to that number. Then what I can do is solve for m, put that on one side, put the other stuff on the other side, and I'll factor out a factor of 3, and I get, so this equation becomes that equation, but we have our friend Euler, who, faces minus edges plus vertices is 2, so this formula turns into that. And I'm simply going to write this as, I have 3 m's, so I can put one of the m's there and put the others there. Then I'm going to think about this quantity. And here, this is just, a little simple counting argument. But if you take the sum over all faces of the number of edges of the face, well, what I've done is I've double counted the edges. So, it's just a classic thing. But, every face is at least a triangle. And so, very elementary argument. And so what that says is this quantity is greater than or equal to 0. So I have this m plus this guy is greater than or equal to 0, so this guy is greater than or equal to m. So, but that's just an m. But hey, I started with m. So, this is one of our favorite things. If I have some nice inequalities that start in the same place, everybody has to be an equality in between. All those have to be equalities, and my faces are triangles. Yes?
Does it hold in higher dimensions?
With I have no idea.
I'm curious about whether this could be interpreted as a statement that, so the only time you could take a polytope and perturb it and maintain the combinatorial type is if it's simplicial, right? Otherwise, as soon as you have it's not a simplex, and you perturb it, you're going to fill that face.
And so the answer is I simply don't know. But what you're saying there might be, the kernel of something in higher dimension. But notice what that's interesting. That says that that there's interesting interactions between this rigidity stuff and the polytope stuff, and so that's one of the many reasons why this rigidity theory is so interesting. Is some of the things it reaches out to.
Yeah, well, like the convexity is sort of it doesn't work there because there's like the bellows conjecture that these non-convex polytopes that move and have.
Right. So the convexity really is critically important to this argument. So now let's talk about the Cayley-Bengger matrix. So I'm going to switch to the complete graph on n vertices. And so in this case, that's that binomial coefficient. That's now the number of edges. And the image of this map was known in the 19th century. And because in this situation, what I'm going to do is, rather than just map to this space, so that's basically, that's all these guys right here. I'm going to actually think about what's now called the Cayley-Bengger matrix, where I put in some stuff here, add some ones there, and then basically make the matrix a symmetric. It's got 0 in the diagonal because, of course, the distance from QI to QI is 0. And then what Cayley proved in 1841 is that this matrix has rank at most d plus 2, so that means that all the d plus 3 times d plus 3 minors vanish. And so basically, here's some defining equations for the image of this map. But then, of course, we're over the real numbers, and so there are also going to be some inequalities, and that was Menger's contribution, was to provide the inequalities. And it turns out that, so these algebraic equations plus Menger's inequalities completely characterize the image over the real numbers. So that's really nice. And it turns out that if you think the right way and do the right stuff, you're basically saying that a related matrix is positive semi-definite. So we're now in this positive semi-definite land where things get pretty interesting. And so even though this is in one sense a fairly uninteresting graph, because after all this is it's basically rigid in all dimensions, but there's something clearly interesting there. And so again, remember that I'm going to call CM is this Cayley-Menger variety, and so rather the CM of Q is this matrix. So that's the Cayley-Menger matrix. So that's what that guy is. And so what I do is, if I'm going to get my equations, I take these entries and I replace them with the variables, and I make it symmetric. So I put this both above and below the diagonal, and then I actually get just the these vanishing of the minors gives me these homogeneous equations, and so I actually get a variety in a projective space of that dimension. And then what's interesting is that if I do a little change of variables, so I sort of have to pick, pick one of the variables, and so I have to make a choice, but once I make that choice and make this change of variables, then what I get is I turn this variety into the variety of n-1 by n-1 non-zero symmetric matrices of rank less than or equal to D. So all of a sudden, some really interesting matrices are beginning to show up, and this is actually a very classically studied algebraic variety. And in fact, and again, my notation is that so here now I'm working over the complex numbers, and so here's this Cayley-Menger variety over the complex numbers, and again it's isomorphic to this other well-studied variety. And it turns out that we actually know its dimension. And notice that number right there, dn minus d plus 1 choose n, that's our number that's cropping up right here. And so that's a number we like to see. And then its degree is a complicated expression of binomial coefficients. And it turns out that in the case of this variety of symmetric matrices, this was worked out by Gambelli in 1905, and then modern proofs were provided in the 1980s using Chern classes and the methods of modern algebraic geometry.
Oh, it's Giambelli.
Giambelli. So how did I misspell it?
G-I.
Oh, there's an I missing. Thanks, Frank. I will make that correction. And then what I'm going to do is I'm going to switch to the affine cone. This is in projective space, so I switch to the affine cone, and so that increases the dimension by 1. And so so that's the dimension. So then if I take a generic affine subspace of that dimension, that's the codimension now. And so then, so the dimension is this, and so when I intersect it with this generic hyperplane, I just get the degree, and so I get that. And so now we have some sort of enumerative information for how a hyperplane meets this Cayley-Menger variety. So that's nice, we like that. And now let's apply this to some frameworks. So this is a result of Borchet and Strinu in 2004. And so what I'm going to do is I have my graph, again, my usual notation, and vertices, and I'm going to assume that it's minimally, and so here let's assume that it has this number of edges. And so notice that that's the case where these numbers are equal. So notice that if I have that number of edges, then when I throw away an edge, so if that's the number of edges, and I remove an edge, I've made m smaller, and I can't satisfy that inequality. So basically, if this guy is infinitesimally rigid, then throwing away an edge, so if it's infinitesimally rigid, it satisfies this, but when I throw away an edge, it can't. So this is now minimally infinitesimally rigid. So this is what we're going to count. And then it turns out that their theorem is that if I have generic edge lengths, then up to congruence, the number of frameworks with the same edge lengths is bounded above by this number. And of course, it's an upper bound because this is counting complex solutions. And as we saw in some of the earlier results, when you do these equations, you actually get a lot of complex solutions. So the number of actual real solutions is probably a lot smaller than this, but it turns out that when Borchet and Strano published this beat existing bounds by a lot. So even though this is not a great bound, it was better than what they had at the time. And then the point is that when I look at the edge lengths, they determine an affine subspace, because this is because the coordinates are indexed by the edges of all possible edges, and when I look at the edges for that set, that determines, that fixes some of the coordinates. So I'm getting a subspace, and then notice that this subspace, because it has, I'm fixing that many edges, so I'm fixing the complementary dimension. So this is one of the L's I could use in the previous slide. And the point is that if these two guys have the same edge lengths as Q, well, this is certainly, and so then if this Q prime has the same edge lengths, well, when I look at my map, it certainly lies in the Cayley-Menger variety, but it also, because it has the same edge lengths as Q, that's exactly what puts it in F. And so this intersection is basically contains all these guys, but so that gives a bound on how many of these guys there are. But of course, because here this is for the complete graph, basically this determines, once I know this, there's only finitely many possibilities in each of this. It determines Q up to congruence because it determines all edge lengths. And so we actually get that bound. Now, it turns out it's not a great bound, and this is where some of the recent work comes in. And so there's a paper that appeared in 2008 in the SIAM. This is the Applied Algebra and Geometry Journal. Remember, I was telling you that you should put your best papers in this. Well, these guys took my advice and put the paper in there. And so what they did is they basically they did a very recursive one, and they're trying to compute realizations over C, but in a way that's more realistic than just that degree bound. And for 8 vertices, they proved that there, and then by looking at the ones over C, then they could try to figure out how many actually work over R, and then they found for 8 vertices, they found 78 realizations of a minimal locally rigid graph up to congruence. And if you look at 8 vertices, the Borchet-Strano bound is a bunch of binomial coefficients, so it's quite a bit larger. So the idea is that, again, because this is counting a lot of complex solutions that you're not interested in. And then another result that's actually was posted in the archive in February of this year. So I know Ioannis Samiris in Athens, and this is some of his collaborators. And so they're basically talking about spatial, so minimally rigid graphs. So they're now working in 3-dimensional space. And so there they used mixed volumes and the Bezout's theorem on a toric variety. They did some very explicit constructions. And then for 8 vertices, their methods gave at most 80 realizations in R3 of a minimal locally rigid graph up to congruence, and then by construction, they actually could show that number sharp. So they actually, I think it was a lot of work, but they did it. And in this case, in dimension 3 for 8 vertices, the Borchet-Strano bound is a little bit bigger. And so again, you have these bounds that we had, and now by some pretty hard work, you're getting better. But the point, the challenge is that, these bounds work in general. And these take very particular methods, and so I suspect that trying to adapt either of these to the general cases can be really tough. And but there's clearly this is really recent work. So this is people that are working on this actively. These folks are based in Austria. These folks are based mostly in Athens. So it really is people all over the place that are interested in these kind of questions. And so the conclusion, just to sort of remind you of what we did, is I talked about the bar and joint frameworks, the bar and body. We talked about what motion means and the various flavors of rigidity. And we saw the rigidity matrix is a pretty good object. And then also we talked about some algebraic geometry, and we had a configuration variety. We actually proved a nice theorem about polytopes, and because in every lecture you're supposed to prove a theorem. I've actually violated that a few times, but at least if you're going to give a week of lectures, you ought to prove at least one theorem. So we have that. We talked about this pretty Cayley-Menger variety, which is going to reappear in the next lecture when we talk about the rigidity Batroid. So this guy's going to make a reappearance, and then we got some interesting bounds. And so for the next lecture, we're going to do some combinatorics. So thank you. So any questions?
Can we go back to the previous slide? I was interested in there was this there were instructions in dimension 3, but not in dimension 2 that I realized the chart.
Yeah, and so the answer is, I think these guys might have, this is their paper on dimension 3. It's possible they have some work on dimension 2 that I don't know. And so I am not remotely an expert in this. So this happens to be 2 papers I happen to encounter, but your question is probably answered by other works in the literature. Jessica, do you know any?
I'm not sure. Are you sure it's not sharp in the?
Yeah, so it's possible that's sharp, and so I'll have to go back and when I write the book, I'll have to go back and look at that paper carefully, because it's possible that that 78 is sharp. Yeah.
Is there a choice of vertices and dimensions for which the Borchardt triangle is sharp?
I would guess that the answer is not remotely possible. I suspect there's, I suspect the maximum, because it's bound over the real numbers, and I would expect that to be, I would guess that it would be far less than the Borchardt Strino bound.
It's hard to know. I mean, for some types of problems, the real number bound is the complex number.
Right.
It's actually quite subtle to find restrictions on it.
Right.
But also very important, because you don't want to be searching for a million things that don't exist.
That's right. But there's the famous tangents to 4-unit spheres problem, where if you want disjoint spheres, how many lines can be tangent, and if you allow the spheres to be overlap a little bit or have different radii, you can get 12. 12 is sort of a theoretical upper bound, but if the spheres have the same radius and are disjoint, the best they found, is it still 8 is the best they found?
I think it's still 8.
Yeah.
You can do 12 if they're disjoint.
That's right.
If one is smaller than the other. But
Right. So even with a number as small as 12, here's a slightly different 3-dimensional problem that's still open. So my guess is, I've done most of my algebraic geometry over the complex numbers, and there's a reason. And I should make one comment about yesterday's lecture, because Frank and I had a conversation during the lecture.
I was completely wrong.
Well, the answer is not really. I'm going to disagree with Frank. Because the idea is that, I had a picture, and I was saying that, it was a tensor product. It was a 3x3 tensor product patch. Frank was saying it was a 3x4 tensor product patch. In a sense, we were both right. We were both talking about the same paper, but we were talking about different versions of the paper. And so in one version it was a 3.4, in the other version it was a 3.3.
Yeah, the referee made a comment which led us to improve the patch to 3.3,
Right.
which is industry standard, and I just forgot the chain of events because I remember the 3.4.
Yeah, well, I mean, it's the kind of thing, do I remember every detail of every paper I've ever written? The answer is no, and Frank's written many more than me, so.
I think you've written more pages.
Let's check that.
So any other questions? Okay, so let's go get some of those caffeine molecules.